So I'll be talking to you all about the sensor payloads. To start off, you have 5 choices: the X1000, the X2000, the X34, and 5000. It should be noted that with each sensor payload, starting from the X1000 and ending with the X5000, they increase in size, weight, power draw from the aircraft's batteries, zoom capabilities, and cost. The sensor payload is an interesting part of the project because it can really make or break the objective function. If you go too much into your cost, it doesn't matter how good your performance is, you've already blown it completely out of the water. And also, the sensor payload almost completely determines the flight pattern and how exactly you're going to search the area. For our UAV, we chose 2 X3000s. The first one would be used for detection. It would be zoomed in at about half of its zoom capability, and that would be our detection camera. You can see on the picture on the right, there is a detection circle, and the blue box in the middle is called a camera footprint. And using the software from the workstation for the SUAS, it will automatically search the area within the circle. The picture on the left is the confirmation area for our second X3000. After an object is detected, we then confirm it with our second camera. It's zoomed in with a wide-angle view of 5.5 degrees. In other words, it's zoomed in very, very far, almost as much as it can go. When you confirm an object after you detect it, you have to take into account how far is this object going to travel while I'm going to confirm it. It takes 5 seconds to do that, and we found that the confirmation circle was large enough that we could confirm an object. It would not go out. So all in all, our combination left us with a large area that we could search. We could cover all of it. It left us with an affordable cost, and mostly it let us further customize the flight pattern, which Justin Wildy will now talk to you about.
Alright, throughout the challenge we were given a mission plan. We have the plane, and there's a missing child. So what do? We design a path that the plane is going to take to search the entire area. The area is consisted of a 2-mile radius circle where the child is supposed to be found. And when we heard this, our first instinct was to design a path that flies out to the boundary and circles inward, covering the entire area. We did this in a reasonable amount of time, about half an hour, but we knew that it can be improved. We determined that the time was a huge factor in the objective function, and we knew we had to minimize that. So through further research and joining teams with the camera footprint people, we were able to find the best option for a path. The path on the bottom is our final path. It's an oscillating function that the plane will go back and forth across the search area, covering the entire area. The gaps are exactly the perfect amount that the camera can swoop back and forth and cover everything that needs to be covered. The sharp edges on our flight path needed to be rounded so that we could decrease the angle of bank, and therefore we were able to fly at a higher speed. This would decrease the time also. And our final time was 0.306 hours, roughly 18 minutes, and this was nearly cut our first option in half. Next, Austin Wofford will talk about the business side of the challenge.
A very big part of the challenge this year was to create a business plan so we could actually market the small unmanned aerial aircraft system that we designed and created. To begin with, we had to assess the market. The biggest competitor to the private sector search and rescue operations now is the U.S. Coast Guard. These operations are very expensive, especially compared to our system. To give you an idea of how much this costs, the operation cost of a standard helicopter is around $1,600 per hour, which compounds very quickly to around $3 to $5 million annually for the 3,600 missions that the Coast Guard does on average per year. This cost is then transferred onto the taxpayer. So by moving this search and rescue operations to the private sector and eliminating government costs, we can decrease cost and also create better, more effective plans for search and rescue operations. Some selling points to make this an attractive option to consumers is its safety. It's an unmanned system, so we have no pilot. Oftentimes in search and rescue operations, there's inclement weather or other dangerous situations. We wouldn't want to, have another search and rescue operation going on because our plane went down. This plane goes down, we lose money, not people, which is more important. It is also a very efficient design. It's lightweight. It's easily transported. Technically, one person can transport this plane by itself. The maximum takeoff weight is around 25 pounds, so it's very easily transported. You can haul it in a truck to the search and rescue zone and easily deploy it and rapidly find the person you're searching for. Usability will only improve from the very small crew that we have now to actually operate it. With further advances in software design and flight mechanics, it will be even easier for one person to operate, which will eliminate operating costs as well as time required to deploy it. Other uses, this could be used to monitor industrial areas or monitor wildlife or just to do research in a private industry. Here's a chart that displays some of our costs, pre-market and at market. Pre-market cost initially is $111,000. That's what it costs to produce this system. And operating cost is around $7,400 per hour or per mission. And at market, we have created a 50% markup to make it a profitable endeavor. And it would cost the consumer around $167,000 to purchase this and put it into action. And we have estimated a likely lifetime of around 50 missions. So by analyzing the usability of our aircraft over 50 missions, we can divide the initial cost by 50 missions and add it to the operating cost. So for a consumer to operate this, it would cost around $9,000 per mission. And this will help us lead into our objective function. As I said, the operating cost, we multiply that by 50 for the objective function given to us by the challenge. So that comes out to around $350,000. And then we'll multiply that by the time that Justin gave us by the flight plan of around 18 minutes. And we end up with an objective function of 113,071.47, which we think is very good for the challenge. We would like to thank you for coming, and if you have any questions regarding technical or specific design specifications, I, as well as the rest of my team, would be happy to answer those.
I'm going to go over here, I think.
High school students. Wow. Does that take your breath or what? It does mine. That's why I love this school. I love our student body. We just, wow, that was awesome. Very excited about being here today. I think we have one last thing we'd like to cover before we leave today. Is that right? We'd like to cover one more thing.